Evening, everyone. Special thanks to Dr. John Matthew, my teacher, my colleague, Dr. Manu, who is moderating this session. Today's topic would be cochlear implant device and electrode. We are going to talk about the design concepts and the types of electrodes in detail. The data is taken from three implant manufacturing companies, the Advanced Bionics, the Cochlear, and the Medal. So my special thanks to all these three implant manufacturing companies. Now we'll start off. So first we'll go to the history. Ever since the multi-channel cochlear implantation has been devised or invented by Professor Grammy Clark from Australia, this is the setup of the speech processing unit and the implant chamber there. Okay, suppose one has received a primitive cochlear implantation, then the person should go to this room to hear sounds. So this is the first person who received the cochlear implant by Clark here in the picture. So his name is Saunders, and here we see Irving Hochmeyer, who established the Medal company, and this is the picture from Innsbruck. So this was in 1978 and this was in 1979. So we have nearly a history of 40 years. So how did the changes happen for the last 40 years? We are going to discuss in detail now here. So first we'll go with the Cochlear company here. So the first thing, the implant has been first done in 1978 and got approved by FDA in 1979. So the speech processor was actually a big unit. Then it changed to a size of a book. And then in 1982, it was like a pocket model. This is a body-worn speech processor and underwent a series of changes. From the body-worn processor, it changed to a behind-the-ear speech processor like that. And again, it changed over a period of time. And what is available right now with the Cochlear is Nucleus 6 processor and Nucleus 7 processor, which is the most advanced. So the changes have took place over a period of decades, and now the processor size has been coming reduced. So this is the behind the ear type speech processor. Now the size has even come down to this level. This is called as Canso processor by the Cochlear. You don't have to wear anything behind the ear, and there is nothing like a social stigma if you grow much hair, and this is attached to the internal speech processor by a magnet link. So this is the only thing which you need to wear as a speech processor here. And on the outside or the lateral aspect, you will have the control button, the microphone ports, which are directional microphones, the air slots to prevent the moisture ingress inside, and on the back side you have the battery chip. Okay, so if you think that this processor is also too big, why don't we go for a cochlear implant which is totally implantable? That means you don't have to wear anything outside. This means there is no speech processor. If there is no speech processor, then how would the cochlear implant work? The sound processor can be integrated along with the implant which is kept inside the body. That means the sound process also goes with the receiver stimulator inside the body. The battery backup and also the microphone is incorporated in the implant itself. So the microphone, the battery, and also the speech processor is combined with the implant here. So this is called as TICI. That means totally implantable cochlear implant. So this is in research stage still, and this is being taken up, this project is being taken up by Cochlear company, which has started in 2018. Maybe in next 10-15 years, we can see this implant coming into the market. So the main disadvantage of totally implantable cochlear implant is the power to drive the internal processor will not be that good Why? Because the battery has to be recharged. That means it has to be replaced after its lifetime or duration. Now, we have talked about the speech processor. Now we'll talk about the receiver stimulator, or also technically called as implantable cochlear stimulator. That means the receiving is from the external link, and it will stimulate the internal constituents of the cochlea, that is the neural elements. So implantable cochlear stimulator, otherwise called simply as receiver stimulator. So this is the receiver stimulator, which is primitive ones, and it has got an electrode. So again, this has transformed over a period of time like that. So CI22, then CI24, then comes the contour, and now comes the freedom. And the latest advancements is say 500 series, 512 series, 532 and 600, and even 632 series. These are called as profile and profile plus. Now, when you see these things, earlier there was no ground electrode. This is the ball electrode or the ground electrode. If there is no ground electrode, this ground electrode can be incorporated in this implant itself, that is in the receiver stimulator portion. Now we'll discuss about the things which are important here. Now, this is about the medal transformation. This is about the external speech processor. The initial ones were Comfort, then came to CIS, then CIS Pro Plus, CIS Link, which has transformed from a body one processor to a behind the ear processor. And then came the Tempo Plus, and a special mention about the Duet, which is the next series. Duet means two. Duet means two. So it doesn't act only as cochlear implant, but it also acts as a hearing aid. That means two modes or bimodal type. So what are those two modes? One is acting as a cochlear implant. Number two, acting as a hearing aid. That means electro, that means cochlear implant. Acoustic, that means hearing. Electroacoustic stimulation. That is the speciality of this Duet processor. Then came to the Opus 1 and Opus 2 series for a very long time. And now we have in the market something called as Sonnet, which is considered to be one of the lightest speech processor to wear. So this will be very helpful in a pediatric population. And then comes the off the ear, that is, it is not placed behind the ear, but it is placed in this region, approximately at a 45-degree angulation from the external auditory canal, 45 degrees towards the away, 45-degree angulation from the Frankfurt's plane at approximately 5 to 6 centimeters distance. This is called as a Rondo 1. And the latest advancement is a Rondo 2, much smaller in size, and it weighs less. And even we see a Sonnet 2 in countries abroad. Okay. Now we'll come to the internal cochlear stimulator of the Medal company. So these are the primitive implant. This is a 4-channel implant. This is a 6-channel implant. This again is it was a C or Combi 40. Then came Combi 40 Plus. Then came Pulsar. Then came the Maestro, Concerto, and Synchrony. A special mention about the Synchrony process. If you can see the magnet here, as compared to the other series, this has got a south and a north pole. When this implant is subjected to a magnetic field, this magnet is going to revolve by itself in its own axis so that it aligns itself in the magnetic plane that is required when it is subjected to the magnetic field, when you have to go for a imaging like magnetic resonance imaging. So this is the specialty of Synchrony process. That means this is MRI compatible up to 3 Tesla strength. And next came the Sonata series. Now we'll quickly jump on to the next company, that is nothing but Advanced Bionics from USA. The initial processor looked something like this, which is called as a Clarion series, Clarion 1 and 1.2. Then came the S series, then came the PSP, that is Platinum Sound Processor. These are all body worn type. And then comes the behind the ear processor, the Platinum, then C2 BTE, and then came the Aurea, and then came the Harmony. This is for a very long time. And then came the NIDA series, available as NIDA Q30, 70, and 90 series. And the Neptune processor is the only processor available in the market which is totally waterproof. All the implants other than this are water resistant. This is the only waterproof external speech processor provided by Advanced Bionics company. This can be worn and the child can swim very happily. So the next one, the latest advancement from the Advanced Bionic Speech Processor is Chorus series. This is not yet available in India. This is available in US, launched in 2019, that is a year back. So what this company thought is not only to advance, but go back to its previous implantees. So the people who have been implanted with the Clarion series, if at all they aren't working, they can upgrade directly to a Chorus external speech processor, which would be compatible to the earlier implantable devices with the Clarion series. So this company has thought about its implantees, which were done a few years back, maybe nearly 20 years back. So this is a good move by the company, and this is also fully waterproof, and this is body-worn speech processor. Now, about the internal cochlear stimulator or the receiver stimulator, the initial series were Clarion 1, 2, and 3. A few are actually not released into the market. They were only for an experimental purpose. And later on came the High-Risk 90K Advantage. Both are High-Risk 90K Advantage series. The one with the gold is a first generation one. The one with the silver ones is a second generation one. And then came the Ultra series, and next comes the Ultra 3D series. So now this 3D series, similar to that of the Synchronous series by the Medal, is also compatible with MRI up to 3 Tesla strength. Even the Profile series or Profile Plus series by the Cochlear company is also MRI compatible. Now there is a competition running between all the three companies. All the three companies have MRI compatibility up to 3 Tesla. High-Risk Ultra 3D from Advanced Bionics, the Nucleus Profile Plus with the Cochlear company, and the Synchronous series by the Medal company. All the three implant receiver stimulators are MRI compatible up to 3 Tesla strength. Now, a short note about the what exactly is over the receiver stimulator, why these all designs. See, you can see a star mark here over the magnet here. So this is the one which indicates the pole, and it should be always directed towards the surface here. Okay, and here is the company information. Company information is divided in such a way that the implant can be recognized by its serial number divided into 3 parts. This is applicable with the Cochlear Nucleus Freedom series. So this serial number is in 3 parts. The first part over here, the second part over here, and the third part over this portion of the implant receiver stimulator. So this makes the entire serial number. If suppose one wants to get some information that is lost because of the loss of the surgical notes, if one takes a plain radiograph, you can again read this, which are radio opaque, and one can say about the serial number, the implant make, and the series when one obtains a simple X-ray or a plain radiograph. Now, if you don't need to go for a imaging, you can also just simply code it by a barcoding here. Now, the latest technology is that you don't even need an X-ray. You can just barcode it. This will give you entire information about the implantation procedure, implant nodes, and the implant series, and the make and everything. This is what we have to acknowledge that the company is moving forward for the advancement of the coding systems. Now, if you have observed over a last 3 to 4 slides, the earlier series of receiver stimulators used to be of this type, and now the latest advancement is this type. You see that the earlier receiver stimulators very small in size, but now it is a little bit bigger in size. Why is there a difference? One can observe the earlier implants are made up of ceramic, but now it is the titanium. Why did they choose ceramic referred to titanium earlier? Is the advantage is that the ceramic implant have a transparency for radio frequency signal. That means the radio frequency signal is the way by which the external processor will communicate with the internal receiver stimulator. So the data is transferred by radio frequency waves. That radio frequency waves can pass through the ceramic implant, but not through the metallic implant. That is the biggest advantage of this ceramic implant. Number two, the electrical thing here can also, and the magnetic thing is, can be incorporated in a ceramic device. That are the advantages of ceramic implant. But why did we change to a titanium implant? Is that the ceramic implant is fragile. There are a few reported cases where there has been a trauma to the head, there has been a fracture of the ceramic implant. And the second reason why is that there may be some moisture ingress in a lower temperature where the water enters the implant, and there will be hydrobiodegradation. At a low temperature in a moist environment, there can be some reaction in the implant receiver stimulator. So these are the two reasons why ceramic implants are taken off, and the place is taken up by the titanium implant. Now the casing here is the titanium implant, under which there will be circuit or the microcircuit. Now the disadvantage of this titanium implant is you need a power source here, which cannot be incorporated inside. Why? Because this is not a radio frequency transparent. This is opaque. The radio frequency waves cannot pass through the titanium. So that is the reason why the coil which has to supply the power comes out of this titanium case, and the input of the power is delivered through this here, and the information which has to go will be exiting here. So this is the entry point of the power and the data, and this is the exit point to the electrodes. So the link has to come out. Once the link has to come out, the size of the implant is bigger in size as compared to the previous implant. But at the same time, this titanium has even less permeability as compared to that of ceramic. Now, what exactly is permeability? Permeability is nothing but the property of a substance to allow the air to get inside or gas to get inside. So the permeability of the metal, and here specifically titanium, is very less as compared to the ceramic. Ceramic are also good, but titanium is more good, and it also doesn't have any brittleness like that of ceramics. That is the reason why the changeover of the receiver stimulator is from the ceramic to the titanium. Now we'll go about the dimensions and the style of the cochlear implant receiver stimulator. So the dimensions is of 4 things here. Okay, the first thing is the length here. This is the length. This is the width. The thickness or the profile is the one here. And fourth one is the angulation. So the length and the breadth are usually to be smaller in size, so that if you have a smaller implant, you need not make a bed for the receiver stimulator. Instead, you can go and do a subperiosteal technique or T-pocket technique that is described by Thomas J. Balcony, which was described earlier in the talk given by us. So suppose if the profile, that is the thickness of the implant that is to be seated into the bed, is very big, and you have to do a pediatric cochlear implantation, it would be difficult for you. So if the profile comes down, that would be easy for us to go ahead and do a subperiosteal technique. That is the reason why nowadays the profile of the implant has come down. That means the thickness of the implant has come down, and now we have a implant thickness which is very less, up to 3.9 millimeter. So you can just drill a bed if required up to 2 millimeters or so, and you can seat the implant. Now there is another way to escape the bed making, that is to just drill the anterior portion of the bed instead of making a full bed, and you can seat the implant by the pins here. So this is called as a pedestal cochlear implant receiver stimulator. These pins will go into the skull where the side of the bed of the receiver stimulator is, and it can sit properly, avoiding a complete bed for receiver stimulator. So we need to know about the length, width, the profile, and whether it is we require a pedestal cochlear implant or not. Now the next dimension is flexibility. So this is the implant here, receiver stimulator, and this is the coil, telemetry coil here. Okay, now this is the silicon made here, the coil external portion. The coil is in fact made by a gold wire. Okay, and this is nothing but a titanium case. So there is an angulation. It's not that it is straight. The coil can be bent at an angulation of approximately 15 to 20 degree. The more the angle, the more you can comfortably seat this implant over an irregular skull bed if you have to make. So this is the flexibility allows the implant to seat it perfectly in a irregular skull bed. That is the advantage if you have more flexibility, which is common with the recent implants and may not be possible with the ceramic implants. Now, a word about the imaging safety once again. So the earlier implants, or the ones which are the high profile series here from all the companies, the other implants, receiver stimulator, will have a magnet which can be removed surgically in case if it is required, if the implantee has to undergo an MRI. If the magnet is in place, still you can go ahead and do an MRI up to 0.3 Tesla. But 0.3 Tesla MRI would not give any information. We can remove that and get a 1.5 Tesla MRI also. To avoid these minor surgical procedures also, the implant companies have come up with a new series of the implants, that is nothing but the Ultra 3D, the Synchrony, and the Profile Plus series by the companies. And these implantees who are implanted by these three implants can undergo MRI without the necessity to remove the magnet. One thing about this Profile Plus series, there will be a small pocket like thing, and the magnet can be taken out in case if it is required, and you can proceed with even a MRI with a Tesla strength more than 3. Now, if there is a ceramic implant and the implantee has encountered some degree of trauma, so that may result in a fracture. If the trauma is less, the implant hasn't break, but there is a displacement of the magnet, then also you can just take a plain radiograph and again keep this magnet in its place or in its pocket. So there is something called as an impact resistance. To how much force does the implant take the impact? So all the cochlear implants will take a impact of force approximately up to 2.5 joules. There is only one cochlear implant in the market which can take the force up to 6 joules, and that is nothing but High-Risk 90K Advantage. The cochlear implant company from Cochlear Nucleus will have an impact resistance strength of approximately 1.0 joules. All the other implants, even the Ultra series, the latest implant, and the Profile Plus series from the Cochlear company, will have an impact resistance as mentioned by the manufacturing company itself is only 2.5 joules. But whereas the high-risk 90K advantage implanted by the advanced bionics has got an impact resistance of 6.0 joules. That means if you hit or if you apply a force up to 6 joules, this cochlear implant receiver stimulator may not face any problem or breakage. That is the impact resistance factor. Now, the external component or the speech processor is something like this. We'll just explain the parts here. So this is called as headpiece, which will have a magnet on the other side, which will attach to the magnet with the receiver stimulator. The link between the external component and the internal component is earlier percutaneous, that means through the skin. So the infection rate is high. Now they have changed from percutaneous, that means through the skin, to transcutaneous, that means through the skin, that is without the skin involvement being punctured or without the incision of the skin or the attachment through the skin. It is a transcutaneous link between the external component and the internal component. This is the headpiece which has got microphones. They can be 1 or 2, and if you have a bilateral cochlear implantee and the microphones can be actually talk to each other, and there can be noise cancellation effect by these microphones. Okay, and this is called as the headpiece cable, which attaches the microphone and the headpiece to the processor here. This is the processor, which will have a battery backup. So almost all the external component or speech processor units will have a battery backup that can be recharged. The rechargeable batteries can be applied, or a special battery which can be replaced can also be applied. So battery which has to be replaced usually are zinc air batteries. Okay, they are zinc air batteries, and this is the program button. Usually we have 1 or 2 or 3 or 4 programs, that is P1, P2, P3 and P4 respectively, which have an indicator to tell whether the speech processor is working properly, or it is reducing in charge, or it is off the charge. We have a volume control. You have a microphone which can talk to the one which is on the headpiece. This is the unit here, and this is called as a T mic, which will be worn at the level of the external auditory canal. So the external component talks with the internal receiver stimulator through the radio frequency link. A simple thing is this one, how it is connected. The sound comes from here, gets picked up by the microphone, is processed in a speech processor, and it is transmitted through the skin into the receiver coil or the receiver stimulator. So the one which lets the data out is called as a transmitting coil. The one which takes the data in is called as a receiving coil. So the skin acts as a barrier here that can be linked here, and this receiving coil will take the information and it will send to the implant processing unit, and that processor will send the signals to the cochlear neural elements via its electrodes. So the link is nothing but the radio frequency here. Why radio frequency? Number one, it is a link which can be a transcutaneous. The data can be transferred very easily without losing any information. That is the beauty of radio frequency signal transfer. Now, one slide about the processing strategy. So there are many speech processing strategies, but most of the implant manufacturing companies now adopt something called as CIS processing strategy. CIS stands for continuous interleaved sampling. There are other speech processing strategies which can be incorporated with CIS, is called as ACE, Advanced Combination Encoding System, and also multi-peak or speak, or it can also go for high resolution speech processing strategy by few manufacturing companies. I'll just explain in very briefly about the CIS strategy here. The sound comes from outside, gets picked up by the microphone. This sound signal is amplified in this amplifier. AGC stands for automatic gain control or auto gain control. The analog to the digital converter can be optional. This signal here, which has been amplified, pass through something called as a band pass filter, and the frequencies are divided like this: band pass filter 1, 2, 3, and so forth. These filters again send a signal to a detector where the sound which is coming from the microphone, which is amplified, has passed through the band frequency and it is encoded in an envelope. That information is sent to a signal processing unit here, which is called a stimulus encoder, that encodes these data or the sound signals and sends into the internal cochlear stimulator. The internal cochlear stimulator will decode that information. This is a encode. That means this will write the code and this will decode the code. So this is called as a decoder. The one is encoder, that which writes the code, and the other one is the decoder that will retrieve the data which is transferred. That data once again will be sent via the electrodes to the cochlear neural elements. So this is how the continuous interleaved sampling works. Now, a word about the sealing system. So we have come from the external processor to the internal stimulator. So this is the starting unit of internal stimulator. So this is the power coil or power receiving coil, also works as a communication antenna, that is between the internal portion and the outer external portion. So these wires what you are seeing are nothing but the gold polymer fibers. So this is a stuttered gold element which will carry the information and enter this titanium case where there is a circuit. So this is the entry point and the processing takes here. This is the decoding process and that information is exited through this link. So this package or this microcircuitry is sealed very tightly in a case of titanium. So how it is sealed? That is called as hermetic sealing. What do you mean by hermicity? The hermicity is nothing but a state of airtightness. If there is some air inside this titanium capsule, there will be some problems. So it has to be airtight. That means there should be only vacuum and not air. So, but the system should be entering and the system should be exiting. These feeds from the input and the exit point that are called as feed throughs. So these go and enter and these come outside. These are called as input and output. These are nothing but feed through. This is the internal feed through and this is the exit feed through. So feed through is the area in the hermetic sealed package where the information comes in and lets out. So this case doesn't have any radio frequency transparency. So this will not get spoiled. Now, how to seal it? There are lot many ways of hermetic sealing. The best of the best is nothing but the laser welding. The other types of sealing are resistant welding, tungsten inert gas welding, that is called as the TIG welding, and the latest one is the electronic beam welding. Of all these four sealing techniques, the best ones is nothing but the laser welding. Why does it have an advantage over the other things? Now with the tungsten inert gas and the electronic beam welding, you need a vacuum to weld it. So in a case of laser, you don't need a vacuum. You can do it in a simple air. So the equipment required and the environment required is more favorable for a laser welding, and the sealing is very, very good in case of laser welding. Now, if there is any entry point that is not sealed properly, the air or the moisture can ingress into the capsule, causing some damage by oxidation or decomposition because of these elements here, that can lead to a electronic circuit failure, that is called as short circuiting. So where does the water or air can enter the system is nothing but through the feed through. So most of the times the exit point is the point where the hermetic sealing fails. Okay, so this is called as a principal failure point. Now how to uh, uh, tackle with this failure point is, if the implant is made in such a way that this and the exit electrode, if they are of the same material or substance, then the sealing is not required. In such a case we can escape these failure points, but right now it is still in an experimental phase. Now we are moving from the receiver stimulator package to the electrode array. Now, what do you mean by electrode array is the part of the cochlear implant that goes into the cochlea is called as electrode array. This is the electrode array over which the electrode contacts lie. So what are exactly these electrodes? These are nothing but wires. These wires which transfer the energy are dimerically removed here in this portion. This dimeric layer is removed, and that transforms a wire into electrode contact. So this is nothing but an electrode contact. The outer chip of the wire is just taken out. Once we remove the dimeric substance from the wire, it converts as an electrode. Once you chip out something, the surface will not be smooth. Instead, the surface will be rough. That is the advantage of this electrode, in that a rough surface will have less resistance. That means the electrical signal will have less resistance to go into the cochlear fluid, that is the perilymph, and stimulate the neural elements or the end auditory nerve fibers. Though so the contact, if at all it is not smooth, will have less resistance, and this can transfer more of the energy. Now to improve the conductance of this electrode contact, we can even apply some conducting substance. Here we see something, electrodes are a little bit black in color. This is called as a conducting substance, and that conducting substance is nothing but called as platinum black. So it improves the conductance of the electrode contacts. Now we have a lot of confusion whether a channel and an electrode is one and or the same. No, a channel is different from an electrode. A channel is nothing but the stimulation site in the cochlea or the inner ear. The more number of stimulation sites, the more the number of channels is. It has got a relation to the electrode contacts, but the electrode contacts and channels are not one and the same. Okay, we have a few number of electrodes which can stimulate a lot number of sites in the cochlea. So a single electrode is not equal to a single channel. The channel means the current should flow from the positive to the negative end, developing an electrode potential. To get an electrical circuit, the current has to come from positive and reach the negative. So, or the vice versa when you have a biphasic stimulation. So, the number of stimulation sites is called as channel, and the number of electrode contacts is called as number of electrodes. So, the channel's number is defined by the range of the frequencies which have to be stimulated. Okay, now we have two types of cochlear implant systems. The first one is the single channel system, which is developed by House, and the multi-channel system, which is developed by Clark. Now, the single channel means only one side of the inner ear is stimulated. All the information which is coming from the external speech processor is delivered only to one side. But we need to stimulate a lot more areas. over the cochlear neural system. We stimulate the different portions of the cochlea and we get stimulated the different frequencies. That is what we are aiming at. So that means we have multiple channel system that can stimulate multiple sites in the cochlea. So the multiple channel system outweighs the single channel system, which is by house. Now what are the advantages of this multi-channel system is it has got a spatial coding. That means a particular number of neural elements can be stimulated. There is called as temporal coding. That is the time at which a single neural element is or a group of neural elements is stimulated. So if you have the temporal coding and the spatial coding, that means your speech discrimination would be better. So if you have this better speech discrimination, it will be more useful. So if you have a better speech discrimination system, that means the ability to hear in a noisy surroundings will be better. So overall, the multiple channel cochlear implant system has overtaken the single channel system in many ways. Now we don't have any more single channel system, it's always the multi-channel system. Next, coming to the parts of the electrode array. This electrode is supposed to be placed intracochlearly. That means it goes into the cochlea from the base towards the apex. So the part of the electrode which is more proximal or which is towards the base is called as base of the electrode. The portion or the tip or the distal portion of the electrode which goes towards the apex is called as apical side of the electrode. Now you have these electrode contacts. These are nothing but the electrode contacts or in simple electrodes. If you observe, you can see 16 number of electrode cochlear electrodes here in a high-res mid-scalar electrode by the Advanced Binaries company. If you carefully observe here, once again, there is a space between two electrodes here. So this distance is called as inter-electrode distance. That is nothing but a contact spacing. You can have 100 electrodes here with very little spacing. That would be difficult. You can have only 4 or 5 electrodes here with a larger spacing. That is also not good. So what should be the ideal contact spacing between the electrode and electrode? That is called as critical distancing. That is nothing but 0.45 millimeter. If the electrodes are very largely or distantly placed, suppose you have an electrode here and you have an electrode here, this electrode will stimulate the neural elements here and this electrode will stimulate the neural elements here. So there will be a few neural elements which will not be stimulated by either this, that is proximal electrode, or a distal electrode if the space is more. That is the disadvantage of placing the electrodes very far. If suppose there is very little distance between this electrode and this electrode, the distance, if at all it is reduced than 0.45 millimeters, what happens? This will stimulate the neural elements like that. This will stimulate the neural elements this way. So there will be a crossover of the electrical stimulation system over a particular number of electrode, particular number of neurons. So there will be a crossover of the neural stimulation. So even placing very distant or even placing very closer is not recommended. There should be an ideal distance between the electrodes. That is called as contact spacing or the critical distancing. So how much have we inserted the electrode inside can be known by something called as these markers. Okay, in a few electrodes designed by a few companies, these markers will indicate the depth of insertion or the length of the electrode that is inside the cochlea. Once you know the blue marker is here or here, that means this distance or this length of the electrode is into the cochlea. This is the advantage of marking system. A few electrodes will have something to hold to introduce the electrode into the cochlea. This is a system to hold the electrode that can be in the form of a wing. It can also be in the form of a stillet in developed by few manufacturing companies. So you hold the electrode with the stillet, introduce it into the cochlea, and then move this electrode and remove this stillet. This stillet holds the electrode straight, and once it is introduced into the cochlea very gently, this will assume the shape of the cochlea like that, and the stillet can be taken out. So these are the parts of the electrode array. To have a particular electrode that can be called as an ideal electrode should satisfy these criteria. If an electrode has been atraumatically inserted, that is the best situation given. So the electrode which can be introduced into the cochlea should have a atraumatic or at least less traumatic cochlear insertion. The electrode should be placed into the scalar tympani. That means an electrode should be an ideal one such that it can be placed in the scalar tympani of the basal turn of the cochlea, so that it is nearer to the neural elements or the spiral ganglion cell population. Now, the electrode should go into the cochlea almost to the full extent of the cochlea, so that it can stimulate the various frequencies. I differ with this. Why? Because the full insertion is not required in all situations. At least 5 millimeters of the apical area of the cochlea should be left. Why? Because we need not insert the electrode into the cochlea right towards the apex or the helicotrema. Why? Because the spiral ganglion cell population or the spiral lamina will not be going to the entire 2 3/4 turns or 2.5 turns or 2.67 turns. It is going only up to 1 3/4 turns. Once you introduce the electrode into the cochlea, the electrode should not come back. That means there should not be any spring action which extrudes the electrode out of the cochlea. The electrode should be more biocompatible. That means it should not have any reactivity with the body tissues. This electrodes should promote various types of stimulation modes that we will talk in detail in the next few slides. And the electrode should be very easy to handle. And in case if it is required, we need to explant it very easily. Is there any such ideal electrode in any given situation? The answer is no. You have to select an electrode which is supposed to be ideal or near ideal to any given situation. Now, how to improve an electrode is to satisfy the points raised for an ideal electrode. So the electrode should be designed in such a way that it will give the spatial and temporal coding well, that is place coding. Now, it should have less trauma to the cochlear tissues or the intracochlear tissues. The mechanical properties should be favorable. The dimension should be acceptable. It should be biocompatible, and there should be less biotoxicity, and it should be easy to insert and easy to reimplant or reinsert, and it should be easy for an insertion technique if at all one has to go with a freehand or AOS or something called as a insertion tool techniques. Now we'll go one by one here. First is current localization and place loading. What that means, if you give some electric current, a particular set of neural elements are to be stimulated. You have to stimulate only the neural elements which you intended to stimulate. That is possible depending upon these factors. These are dependent on 4 factors. Number 1 is the type of the stimulation, the site of the placement of the electrode, the electrode contact, and the length of the electrode. We'll go in detail one by one. There are 4 types of electrical stimulation or modes of stimulation. 3 types of modes of stimulation. The first is the monopolar stimulation. Monopolar means one acts as a positive, the other will be acting as a negative, completing the circuit. That one will be on the electrode contact inside the cochlea. The other can be any electrode or a distant or a reference electrode or a ground electrode. That is called as a monopolar stimulation. With this kind of stimulation, you will have more number of channels. The more number of channels, the perception and the speech recognition will be very, very good. If these stimulation are adopted, this will require less consumption of the power. If the consumption of power is less, automatically the battery will be lasting longer as compared to the other modes of stimulation. If suppose the electricity flows from one electrode to the other electrode, be it be very close or be it be distant. So if the electricity flows from one electrode to the other electrode, that is called as bipolar stimulation. This can be close or distant. Once this is close to the basilar membrane, if it is a molded array, which will have a good localization. The third variety is common ground stimulation. Common ground, that means the ground is common. The ground is formed by rest of the electrodes, and the other electrode, which is the main electrode, will act as a one end of the electrical circuit. So one electrode is on the positive and all the other will want to be on the negative. This is called as a common ground stimulation. Of all the three stimulation modes, the best is monopolar stimulation, and all the three manufacturing companies which are FDA approved will go with monopolar stimulation. This is the ideal mode of stimulation that is recommended. The monopolar stimulation with biphasic currents is the best mode of stimulating the implantable, electrode in the cochlea. We can also talk about something called as tripolar stimulation and also quadripolar stimulation. That means 3 poles and 4 poles. These are given by advanced bionics, but these would not have any better advantage or edge over the monopolar stimulation, and the speech recognition will not be that great, or speech discrimination scores are not that great with the triphasic or tripolar or quadripolar stimulation. So they are abandoned. Now, a simple diagram here to show the means of stimulation modes here. So if one electrode is connected here and the other would be a ball electrode here, this will make a loop here. So this circuit is called as monopolar stimulation. If suppose this is to the electrode here, reference electrode, this will be another monopolar stimulation. If the electrodes are connected on the electrode array, if it is for a closer electrodes here, there is no electrode between this and this one. So this is called as BP, that is bipolar stimulation. If suppose the electricity flows from this electrode to this electrode with one electrode in between, that is called as bipolar plus one. That means one electrode is left out. If 2 electrodes are left out, it is called as bipolar plus 2. If 3 electrodes are left out, it is bipolar plus 3, and so forth. The common ground means one acts as one end of the electric circuit, all the rest of the electrodes act as the other end of the circuit. This is called as common ground stimulation. Next, a short word thing about the current steering technology. Here, this is supposed to be an electrode, and this is the electrodes on the array. This is the electrode contacts, and suppose these are the neural elements. What happens if you connect or pass the electricity through the electrode array? This will give the current to this set of neurons, and this electrode will give some stimulation to this portion of neural elements. Suppose by any reason this electrode doesn't work, what happens to these neural elements? This will not get stimulated, obviously. So in such a case, you can still stimulate these neural elements by this electrode by steering the current. This is called as current steering technology. This is available with advanced Vinex's new implant systems. So this is how the neural elements get stimulated even if one or two electrodes are not working. Now, where to place the electrode inside the cochlea? We know that the electrode has to be placed inside the scala tympani of the basal tone of the cochlea. Why? Because the electrode will be very nearer to the spiral ganglion cell population. There is a situation where you can still stimulate the intracochlear neural elements by drilling some holes like this, that is making cochleostomies, a number of cochleostomies like this. These are 12 in number. This is done by Choward in 1976. So this is called as multiple cochleostomy. Okay. Now you can also stimulate the neural elements right in the modulus here. So that is called as intramodular placement of the electrode. You can also stimulate the neural elements, not drilling into the cochlea, but making a small hole like thing here, like a gutter, and keep a ball kind of a electrode here and stimulate the neural elements. So you are not going to damage the endosteum. The endosteum is still intact, but you are placing the ball electrode over the surface of the endosteum, and that will pass the current through the endosteum into the cochlear fluids and ultimately into the cochlear neural elements. So this is called as extracochlear. That means the stimulation is from outside of the cochlea. That is called as extracochlear stimulation. That is by Banafi in 1984. Now, this is the cross section of the cochlea. So this is the medial most portion and this is the lateral most portion. This is the superior portion. This is the inferior portion. So this is the scala tympani. This is the scala vestibuli, and this is the scala media, and this is the resinous membrane. So this is the osseous spiral lamina, and this is the spiral ganglion cell population. This extends like this. This is a basilar membrane here. So this basilar membrane has got the hair cells, the outer hair cells and the inner hair cells here. And this is nothing but the tectorial membrane. So these are nothing but the outer cochlear wall, which has got the stria vascularis here. You can see the layers of the stria vascularis here. So if at all you have to place an electrode into the cochlea, the ideal site would be scala tympani. In the scala tympani of the basal tone of the cochlea, you can keep the electrode very close to the spiral ganglion cell population over here, that is towards the modulus. This is called as perimodular placement. You can place just beneath the spiral ganglion cells and the end auditory nerve fibers. This is the D situation here. And you can place the electrode towards the outer lateral wall here. So this is called as lateral wall placement. If suppose you place the electrode towards the modulus or the perimodular, the current required here to stimulate the neural elements here will be less. So the more localization would be there, and the power generation required to stimulate the the end auditory nerve fibers would be less. So less the power consumption, the more battery life. So this will be the ideal situation. But why are we not resorting to perimodular placement is this, once the electrode is placed very close to the modulus, it may hamper the venous circulation. In the earlier talk on anatomy, we have talked something about the spiral modular vein that can be traumatized, and there might be some venous stasis as described again by Thomas Balcony that can cause adverse effects following the implantation procedures and can compromise on the outcome. So that is the reason why we are not favoring the perimodular. What if we place the electrode away from the modulus, that is very distant from the modulus or the spiral ganglion cell population here. That is the lateral wall electrode. Suppose you place a lateral wall electrode, the current has to travel from here to here to stimulate the neural elements here. That means the power consumption will be more and the battery life will be less and the discrimination will be less. At the same time, the complications will be less. Again, the complication of inserting a lateral wall electrode is can damage this portion. Now, if you place a perimodular electrode, this can be damaged. If you place a lateral wall electrode, the lateral wall can be damaged. The stria vascularis or the spiral ligament can get injured. So it is not favorable here. It is not favorable here. You can go in midway. That is called as mid-scalar position. So if you go near the modulus, that is near the spiral ganglion cell population. Just beneath the end auditory nerve fibers, that is deep position. If you are away, that is called as lateral wall. And midway between the two is mid-scala. So you even have a mid-scala electrode that can go right exactly or almost exactly into the mid portion of the scala tympani, at least in the basal turn of the cochlea. So this is what we have already discussed here. And a thing about the biotoxicity and the biocompatibility. The electrode which is kept inside the cochlea should be more biocompatible and have less biotoxicity. So what material we use is nothing but the silicone rubber to carry. That is, the silicone is nothing but a medical grade silicone which has a very good biocompatibility. It doesn't react or it reacts very less to the body tissues. So the biotoxicity is examined for cytotoxicity, mutagenicity. That means that there should be no mutations from there on. There should not be intracutaneous toxicity. The inflammation, when you keep an electrode inside the cochlea, should be as less as possible. And this has been tested in rabbits. So there have been some human studies also, and it states that the chronic electrical stimulation by placing an electrode intracochlearly will not have any adverse effect, even though if it is stimulated for a very long time, like years. And this is entire packaging system is sterilized by ethylene oxide. Now, a word about the electrode contacts here. See, this electrode contact is either made by platinum or it can be mixed up with a part of iridium, that is called as platinum iridium alloy. Most of the manufacturing companies these days adopt the platinum iridium alloy as electrode material or contact. Now, how much of platinum, how much of iridium? Platinum is 90%, iridium is 10%. What is the idea of adding iridium to the platinum? Number one, if the iridium is added to the platinum, the dissolution of the platinum will be relatively less. Why? Because the charge density will be less and the conducting system or capability of the electrode to deliver more current will be there when the iridium is mixed with platinum. That is the reason why most of the companies these days go for a platinum iridium electrode contacts. The electrode contact can be flat like this or it can be ball like this. If you insert a flat electrode contact, the capsule will be formed like that. In case if you have to go for a revision or a reinsertion, you can easily remove it having the capsule intact. Suppose you introduce a ball kind of electrode, the capsule will be formed here, and once you remove the ball, there will be the capsule will get distorted and the reinsertion of the electrode may not be that easy. So always a smooth electrode contact like this is more favorable for reinsertion procedures as compared to ball electrodes. Now, how much should be the distance? How much should be the width? How much should be the area? If it is very small, if the electrode contact is very small, the charge density will be very high and the platinum will come out. That is, dissolution of platinum might happen over hundreds of years. If it is very large, then if the electrode contact is very wider, it will stimulate lot much of neural population. That means more than the neural population than it is required. That means localization will be affected. The ideal width should be 0.3 millimeters, and the inter-electrode distance, which I was mentioning, should be ideally 0.45 millimeters. Now, a word about the length of the electrode. If suppose the length of the electrode is measured, that is from the tip or the distal portion to something called as jog or band like thing here. So this is the total length of the electrode, which is given by the buffer length, which is nothing but the length of the electrode from the jaw to the first stimulating electrode or the proximal stimulating electrode. This is called as the buffer length, and this distance between the proximal and the distal electrode is the region which actually stimulates the intraneural elements. So this length is called as active stimulation length. So this is the region of the electrode array which actually stimulates the neural elements. So this is called as active stimulation length. So when you combine the buffer length and the active stimulation length, you get the full length of the electrode array. And why should you have a buffer length is, number one, the neural population does not start right exactly at the round window. Okay, it will be a little bit distant away. Why? Because the cochlear nerve will be coming a little bit laterally inside the modulus and then stimulating the modulus laterally. Okay, from the modulus towards the lateral wall, the neural elements go. Okay, so if there is a buffer length, that distance can be covered. Also, if there is a buffer length, this length, if at all it is left out outside, will not cause any extra auditory effects like stimulation or tics. Okay, it will not have any neuralgia. So it is always to have some length which can be placed just outside the cochlea. So this will prevent extra auditory side effects. So we have lot many kinds of electrodes. The longest and the shortest are available with metal. The longest electrode available is of length 31.5 millimeters. This is by metal standard series, a classic series, and this is called as a compressed electrode, which is approximately only 15 millimeters, and the active stimulation length is only 12.1 millimeters. This can be used when you have a smaller cochlea or you desire to stimulate only the proximal portion of the cochlea or the high frequency zones. That is nothing but the partial insertion or hearing preservation technique. Now, if you have such a big length of electrode, why should we not go and introduce it full in the cochlea? Why? Because the spiral ganglion cell population will not be up to this length. It will only extend up to 16 millimeters, not up to 35. So it is only 1 3/4 turns the spiral.
Hello, Satyakiran sir.
Can I continue from here?
Yeah.
Okay. Now, if suppose you know the cochlear duct length and you know the ASSR findings, you can stimulate only the areas which you think that you need to stimulate by ASSR and knowing the cochlear duct length. So to cover all the speech frequencies from 500 to 4000, if at all you stimulate, that is more than enough. Anything more or less would be great. Okay. Now coming to the types of electrodes, depending upon the site of placement, they can be placed towards the lateral wall. Those are called as lateral wall electrodes. Those which can be placed towards the modulus are called as perimodular, and they can be placed midway. This is called as median. So examples of the ones which go onto the lateral wall are nothing but the advanced bionics 1J electrode. All the metal electrodes are lateral wall electrodes, and the Cochlear 24 REST. If you want to go for a perimodular electrodes, the example would be Cochlear Contour Advanced, Modular Research Array, and Advanced Bionics Helix. The mid is always a Advanced Bionics mid scala. So simple thing to know, all the lateral wall electrodes are given by metal. So metal has got the electrodes which are all lateral wall. The AB mid-scala electrode is the only electrode which is median place. So easy to remember. Metal electrodes, all lateral wall, AB mid-scala, median. There can be a mix-up of the rest. Now, depending upon the curvature, whether it is a straighter electrode or it is a curved electrode. The curved examples are again 1J, mid-scala, the CI 512 by Cochlear company, and all the metal electrodes are straighter. All the AB electrodes are pre-curved. Once again, I repeat, all the metal electrodes are straight. All the advanced bionic electrodes are pre-curved. So there is a mix-up from the Cochlear side. So this is the example of a pre-curved electrode, and this is the example of a straighter electrode. Now, a word about half-banded and full-banded. So if you suppose take a electrode from Cochlear company, this is 24 REST, which has got 22 electrode contacts with proximal 10 stiffening rings. So this electrode contact is in total like a ring. This is called as full banded electrode. Suppose if they have only on one side, that is called as half banded electrode. Suppose you have half banded electrodes on both sides, that is called as half banded electrodes paired. If suppose you have all the half banded electrodes paired and the distal portion has got only one side, that is called as a soft tip technology. So you have full banded, you have half banded, you have half banded pair, and a combination here, half banded pair and half banded single. Okay, so suppose if you stimulate a full banded electrode, the current will flow in all directions. Why? Because it's like a ring. If suppose you stimulate a half banded electrode, the electricity flow will be only towards one side. It should be towards the modulus, but not away from the modulus. So that means the current which is utilized is stimulated here only and directed towards only the neural elements. Whereas in a full banded electrode, the electricity disperses like this. That means there may be a loss of power here delivered through a full banded electrode, but it has got its own advantage in a given situation. Now, if suppose you stimulate this kind of a paired electrode, the electricity will flow like this and stimulate the neural elements here and over here. And the same situation over here, and in the distal portion of the electrode, the electricity will flow only towards the neural elements here. So every possibility is satisfied here. Now, where is the situation where one would like to go ahead with a full banded electrodes? Suppose in cases of cochlear anomaly like a common cavity deformity or a incomplete partition defect anomaly, where the neural elements are not directed only in the modulus, but it can be distributed elsewhere. There you don't know whether the neural elements is towards only the modulus, which may be absent in such situations, or it can be directed towards the lateral. In such a situation, you can go with a full banded electrode where the electricity flows through all the directions and will stimulate the possible existing neural elements in a case of a common cavity or an incomplete partition defect. It should not be used in one particular situation, that is nothing but cochlear otosclerosis. Now, if you have a paired electrodes like this, half banded paired electrodes, this forms like a one pair and this forms like a one pair. A1 and A2, this is half band, this is half band, this is half band, and this is half band. Now, if you stimulate A1 and A2, this is called as radial stimulation. If you stimulate A1 and B1, this is called as a longitudinal stimulation. Of these two, the radial stimulation here in this fashion has got better sound localization and better current localization. Suppose if you insert the electrode from the base towards the apex, that is called as antigrade insertion. Suppose in a situation where you cannot insert the electrode from the base towards the apex, you can also introduce the electrode from the apex towards the base, that is from the enter the middle turn of the cochlea by a middle turn cochleostomy and introduce the electrode from the middle turn towards the basal turn. That is called as retrograde insertion. The insertion when it is antigrade will cause less trauma to the cochlear walls. Why? Because the scala tympani will have more wider in the apex, and as it goes towards the in the base, and it will have less dimension and it will be more triangular towards the apex. So as the electrode proceeds from the base towards the apex, the scala tympani dimensions would be less. So if you go with the antigrade insertion, the chance of damaging in the proximal segment of the cochlea would be less. If suppose you go for a retrograde insertion, because of the dimension of the scala tympani which is relatively less, there will be more trauma. So retrograde insertion might cause more trauma. So in such situations, what to do? Now, you can go for a something called as double array insertion or double cochleostomy. That means you do a conventional or a round window cochleostomy in one normal sitting and the same one more cochleostomy in the middle turn. So that is called as a double cochleostomy, which is usually done in a case where there is cochlear ossification or cochlear fibrosis. Here are the examples of the double cochleostomy electrodes given by both Medal, which is called as a split electrode, and called as double electrodes in case of Cochlear. If you suppose look at very close look at these electrodes, there is a distance between this electrode and this electrode to demarcate this electrode from this electrode. So this has to go inside the basal turn and this has to go into the middle turn. So this cannot be introduced into the middle turn and vice versa. Similarly, if you see this and this electrode, you see a lot number of electrode contacts for this electrode and you have less number of electrode contacts here. So this goes proximal, that is in the basal turn, and this goes into the middle turn. This should not be exchanged as we wish. Now, most of our electrodes are free-fitting electrodes. That means once you insert the electrode into the cochlea, there will be some reaction of the intracochlear tissues and there will be a fibrous capsule form on the periphery of the electrode. If you introduce a molded array which is very quite thick, that can damage the surrounding cochlear structures. The stiff wire electrode is not available right now. This is the house one channel electrode system where it can cause trauma to these neural elements inside the cochlea. And the reimplantation process will be difficult in case of molded arrays. So a word about the stiffness of the electrode. There is something called as finite element modeling. Suppose you introduce an electrode intracochlearly. If you apply pressure here, this electrode moves inside. But as the electrode proceeds onto the cochlea, at one point of time, it can touch on the lateral wall or it can touch onto the medial wall and the electrode can cause trauma here or it can bend. That stress strain response is studied. So there is a picture. This is a single wire implant of the house and this is a multiple channel implant. So this is the apical portion of the electrode and this is the basal portion of the electrode. we are introducing from here. So if you apply the force here, because of some properties like elasticity where the bend, and there will be some plasticity due to which this area of the electrode will be under a stress called as buckling stress. So that would be less in case the electrode is not single contact, but there are few wires. This is a electrode which has a lot number of contacts. So the distal contact, which will have only one wire, the middle portion will have wires up to that, and the proximal portion will have lot many number of wires. So the stiffness is more here, relatively less here, and relatively very less here. That means the electrode is connected to the electrical system via one wire. So here it will be less number of wires, here will be a little bit more, and here it will be full number of wires here. So the stiffness is more here, relatively less, and very less here. So this stiffness is graded, that is called as graded stiffness. So if there is uniform stiffness like a single electrode, say contact, so if you introduce the electrode inside the cochlea, at one point contact on the perimodular region, there will be stress and trauma here. So if you introduced a uniform stiffness electrode whose tip is very flexible, that is a flex tip technology by metal company, where the proximal portion is paired half banded electrodes and the distal portion is only single half banded electrodes. So the tip is easily bent, but not the proximal portion. In such situations, the force will be more on the outer lateral wall. So this is not good, this is not good. So if you have a graded stiffness, this will be the one which is desirable. It will not cause any trauma, or relatively less trauma will be there in the perimodular region or in the outer lateral wall. So we should aim at having an electrode which has got a graded stiffness. Suppose there is a requirement of reinsertion, or a case where you need to go ahead with a revision implantation, the ball electrodes will be more traumatic while removal as compared to the flat electrode surface. So how is it possible is, if the electrode is placed towards the periphery, that is outer lateral wall, or in the center of the scala, there is a fibrous tissue formation, and that could prevent the revision implantation, where you need to go and stimulate the spiral ganglion cell population. You need to place the electrode more closer to the spiral ganglion population, which may not be desirable, which cannot be achieved, sorry. So if you have to implant prior, better go with a reasonably thicker, I'm not saying a very thick electrode, but reasonably thicker electrode would be an ideal situation. Suppose this is the initial electrode dimension, then after introducing in the cochlea, there will be a fibrous capsule formation. Once you have a situation where you need to reinsert or do a revision surgery, you are going to remove this initial electrode like this. Once you remove this electrode, the fibrous capsule will be there, and you can introduce an electrode either of the same dimension or a lesser dimension. You can't use an electrode of a dimension more than the initial electrode. Why? Because the fibrous capsule will be preventing the entry. So you need to initially use a reasonably thicker electrode, and in the revision surgery, you can go with an electrode of a samer dimension, or you can go with a less thin electrode. So once you introduce the electrode into the cochlea, this is the electrode, this is the scala here through the round window here. First thing is there will be protein absorption here. There the leukocytes will get edited, and over a period of time monocytes and macrophages will stick here, and there will be a fibroblast formation, and there will be a fibrous capsule formation here. This is the ultraviolet microscopic picture where you can see the spiral ganglion cell population. This is the scala tympani, this is the scala vestibula, and this is the scala media. This is the tectorial membrane, this is the osseous spiral lamina, this is the basilar membrane. You can see fibrous tissue or capsule formation here which is just about to form on a electron microscope here. Now, how can we introduce an electrode intracochlearly? You can introduce it with a free hand using some instruments called as claw and Javeller's forceps. This is a claw and this is called as Javeller's forceps, which prevent the electrode being traumatized during its handling. A technique given by Cochlear is called as AOS technique. AOS stands for Advanced Off Stylet. The insertion strategy can be also be done with something called as a insertion tools, which is available with advanced bindings. What is the advantage of using a insertion tool over the freehand insertion? Suppose there is a situation where a junior implant surgeon has to do a cochlear implant. The stability by which one can hold the electrode may not be that great. So that comes by experience, number one. So it will be easy for a beginner to use an insertion tool. The second point is we have something called as a resting tremor. Suppose we have the hand like that, and even though you don't see the hand shaking, there will be minor tremors which will be still physiological at rest. That tremor can cause some trauma when you introduce the electrode inside the cochlea. That can be relatively lessened when you use a insertion tool. This is the engineering behind the manufacturing of insertion tool for electrode insertion. Okay, this is a small video here. This is a freehand technique and this is the insertion tool technique. So I'm sorry. So this is by a freehand in a model here. So this is how it is held. Is actually a wrong way. You can't hold the electrode at a right angle. You have to hold with a Javeller's forceps along the longitudinal direction. You need to hold it this way. You can't go and hold it in a perpendicular direction. This is held with a stillet here. This is the mid-scalar electrode and this is being pushed here like that. And in insertion, while using an insertion tool, this is how it is introduced, and once the insertion is complete, the insertion tool lets off the electrode intracochlearly. Now, a concept about hearing preservation. There might be a situation where you need to stimulate only the higher frequencies. Why? Because those are the frequencies which are usually lost, and most of the times hearing is preserved in apical regions, that is lower frequencies are preserved. So in such case you can go with something called as a hybrid implantation procedures or hearing preservation technique, or also called as electroacoustic stimulation, where the higher frequencies are taken care by the cochlear implant, the lower frequencies are taken care by the hearing aid. You can also preserve the hearing in a normal situation. You should do hearing preservation surgery. You can introduce a reasonably shorter length of electrodes, or you can also use a standard length of electrode but introduce only partially, not fully. So once you go ahead with a shorter electrode or do a partial insertion, obviously the traumatization to the apical regions of the spiral ganglion cell population will be less. So we have something of a length approximately 16 or 15 millimeter electrode length, and the shortest is compressed electrode array given by Medal company. Now, how to minimize the intracochlear trauma? So if you minimize the drilling, that means if you resort to round window technique or extended round window technique as compared to doing a cochleostomy, that means you are minimizing the trauma. If suppose you have to do a cochleostomy in a situation where it is demanded, that cochleostomy can cause trauma by three mechanisms. One is by mechanical trauma. That means once you use a burr over the cochlea, a diamond burr, it will cause some vibration of the cochlear tissue and the intracochlear fluids that can cause damage to the basilar membrane. So that is called as mechanical trauma. Once you use a diamond burr over the cochlea, it will generate a lot of heat, though you irrigate intermittently. So that will be a thermal trauma. The third will be a acoustic trauma. While drilling, the sound generated will be of intensity approximately 130 dB. Even this can traumatize the intracochlear tissues. Suppose you have to use a stylet based electrodes like this, then in such situations also you might require a larger cochleostomy. How to reduce the trauma to the lateral cochlear wall? You can go with a AOS technique or an advanced off-stellate technique given by Cochlear company. The perimodular electrodes would be better, causing no or less trauma on the outer lateral walls. When you go with a straighter electrode, do not go with a deeper insertion, because the deeper insertion may cause the damage to the surrounding structures intracochlearly. If you desire the stimulation of the apical elements of the cochlea, then you can go with something called as a flex tip technology given by Medal. Here, if you see, the distal electrode will have only one wire. This wire is not straight, instead it is like a wave shape. If you see the second wire, the wires are two, the one supplying this and the other supplying this. So there are two here. If you see the third distal electrode, there are three wires, one supplying this, the other supplying here, and the third supplying here. So as you proceed towards the distal portion, the number of wires which is in the waveform are less. So this is more flexible, this is less flexible, this is more less flexible, and this is very less flexible. So this is called as soft tip technology. This is desired when you have to go and insert the electrode very deeper in towards the apical regions of the cochlea. Now, there is a classification to describe the electrode insertion trauma. This is given by Eshraghi in 2003 itself. So grade 0 is no trauma. That means your electrode hasn't caused any trauma. Grade 1 is elevation of the basilar membrane. Grade 2 is rupture of the basilar membrane. Grade 3 is dislocation of the electrode into the scala vestibuli. And grade 4 is fracture of the osseospiral lamina or the modulus or the stria vascularis or the spiral ligament complex. So as you go deeper into the cochlea, the dimension of the scala tympani, initially it will be very large towards the apex. As we go towards, at the base it will be very larger. As you go towards the apex, the dimension of the cochlea will, dimension of the scala tympani will be less. Initially it will be rectangular or quadrangular, and as you go towards the apex it will be triangular. So the dimension has come down, the space has come down. So the more deeper you introduce, there is a chance scala vestibuli eroding or fracturing the osseospiral lamina or basilar membrane. So this is a picture here which shows no trauma to the intracochlear tissues. This shows an elevation here of the basilar membrane, that is grade 1, and here you see the fracture of the osseospiral lamina and the basilar membrane here. Okay, this comes under grade 4 category. So there is one more classification called as modified Eshraghi classification. There's a little bit of a difference between this original and this modified classification. Here the grade 2 says there is a rupture of basilar membrane or spiral ligament here, but the spiral ligament complex injury is graded as grade 4 in original Eshraghi classification. So this is the original, this is the modified version. Whatever you want to choose you can, but you mention that. Now how to number the electrode contacts. So in the advanced bionics and the Medal company, The electrodes are numbered from the distal towards the proximal. So they are numbered from distal to the proximal, from 1 towards 16 and 1 towards 12 pairs here. But it is the reverse order in Cochlear. So the proximal is numbered 1 and the distal is numbered 22. And these are the set of stiffening rings. Okay, these are not active electrodes here. These are only the stiffening rings. So for the advanced bionics and the medal, it is from the apex to the base. So how to remember? AB stands for advanced bionics. AB stands for apex to base. The Cochlear is reverse. Okay. Now, the recent advances, I'll just quickly go through. This is a electrode insertion technique. To prevent the insertional trauma, you can use a robot which is haptically controlling the pre-programmed path. The program is given to the system and it is executed by a Autobot here, and the planning is based on the pre-op imaging technique. So here the impedance is measured when you are inserting the electrode. That means real-time impedance measurement is shown on the screen. In a normal situation, the electrode impedance measurements are taken once you insert the electrode fully, and then you go for electrode impedance. But here in this situation where you use a robotic device, a real-time electrode impedance can be measured. The insertional trauma will be more towards the apical regions beyond 25 millimeters. The next thing is modular research. This is no more actually a recent advance. This is given by Rob Briggs from Australia in 2011. Here, instead of using a stylet based technique, here we use a sheath, which is external sheath. So you introduce the electrode along with the sheath into the cochlea. Then you push the electrode here and you remove the sheath. This is called as modular research array, which is a prototype. Now that the CI532 and CI632 are based on this prototype, they are nothing but a contour advanced techniques, electrodes. So what is the advantage of adding an external sheath and taking out the stellate is, once you take out the stellate, the weight or the dimension of the electrode will come less. The weight of the electrode will be less. So there are 4 issues which are addressed in modular research area. If suppose you introduce an external sheath and not using a stellate, is it causing more trauma or it is the same trauma or less trauma? Can the sheath be easily removed without any trauma while removed? Can it be introduced to the round window technique? No, it cannot be introduced. It has to be going via a cochleostomy, a reasonably shorter cochleostomy, approximately around 1 or 1.2 millimeters to the newer electrodes, and the tip to base diameter is approximately 0.3 to 0.6 millimeter diameter. So, and the fourth issue is this modular research array favorable in a cochlear anomaly? Yes, it is. The other thing is magnetic guidance of cochlear implants. There's a paper by James Clark here. So as you have to guide the electrode deeper inside, you can guide the electrode under magnetic field, which can be applied from the head end of the patient here, and you can direct the electrode. Why? Because the electrode tip will have a ferromagnetic substance here. The tip will be directed intracochlearly, intrascala tympani, not to cause any trauma into the cochlear lateral wall or the medial wall or the superior wall. This will be directed only in the scala tympani as you go towards the apex, which is beyond 25 millimeters. So you have 2 techniques here. One is called as maximal field technique, where the distance between the magnet which is manipulating the intracochlear electrode, the distance, if it is lessened, the field will be more. If you increase the distance between the electrode and the magnetic manipulator, the field will be of a lesser strength. The second thing is called as maximum torque method, where the torque can be achieved by the magnetic field applied at 90 degree or perpendicular. So as you go deeper, this torque will be less. The third thing is shape memory polymers. So the cochlear implant, if it is made out of a shape memory polymer or an alloy like nitilol. Nitilol combines nickel 55% and 45% of titanium. So once you have a electrode which is at a certain shape, when you subject this polymer to heat, the shape changes. That means the shape changes as per the temperature. That is called as shape memory polymer. So once the electrode is straight, when it is introduced into the cochlear tissues, it will be at a temperature of 37 degrees centigrade. So at a temperature of 37 degrees centigrade, this polymer will actually bend and attain the shape of the cochlear spiral. This is the advantage of shape memory polymer. So there are two forms here. Martensite is the softer form, and once you apply the temperature, it will attain a harder form called as austenite. Okay. The other thing is drug eluting electrode or drug releasing electrode. We have heard about the drug eluting stent. Similarly, we have drug eluting electrode. If suppose you introduce an electrode into the intracochlear tissues, there will be certainly some grade of inflammation. To reduce that inflammation, we can add or deliver a drug, something like a corticosteroid, like a dexamethasone, or else a triamcinolone, which will reduce the inflammatory process, thereby reducing the intracochlear inflammatory process. So this drug can also be an antibiotic, it can also be an antioxidant, it can also be a growth factor like brain-derived growth factor or a neurotropin 3, which will be a favorable growth factor for a spiral ganglion cell population. So there is still in the experimental stage with the Cochlear company here. And the last one is a microfabrication technique. Presently, what we are doing is we are making the electrode with the hand. We are welding these, and each electrode has got a wire like that. So if suppose the cost has to come down, the cochlear implant price is huge. So if you have to cut down the expenses, instead of making with a hand, you can go and resort to a machine made implant. So this is called as a microfabrication technique. Electrode is introduced into the silicone rubber sheath. So if at all this comes, then the cochlear implant would be very, very cheap. So this is still in the experimental phase in the human trials, and this is from the University of Michigan at 2016. Okay. Now we have discussed about lot many electrodes here. So what are the ones which are available? We have lot and lot number of electrodes. Advanced Bionics company has got high focus helix, which is now taken off the market. It is having now 1J, mid scalar, and the newly introduced slim J electrode. So you can use any of them. You have the Cochlear company with split array or a double array, which is for cochlear ossification or labyrinthitis ossification. 24 REST, a full banded electrode. For the shorter length of electrode, you can go with a hybrid series or a slim straight 422. You can also give it a higher profile series 522, and all these 522 and the 622, 422 are a straighter electrodes. If you go to something called as 532 and 632, these are curved. These are similar to your modular research array. These are nothing but a contour advance here like that. Now coming to the medal, it has got the largest range of electrodes in its portfolio. The classic ones are of three forms. This is the standard series. Classic forms, it is approximately 31.5 millimeters. A medium one, which is somewhere around 24 millimeters, and a shorter one, which is called as a compressed electrode. In a situation where you do a cochleostomy or a round window insertion and you encounter a CSF leak, where you have to stop the CSF leak with a piece of muscle tissue or fascia, you can do with a special electrode made specially for a special situation where the CSF gush or ooze is expected. So this, you have a cork like thing here. This is called as form series. It is available as form 24 and form 29. Is something called as a flex tip technology, where the distal part of the electrodes is only half banded single. So the proximal portion is paired half banded and the distal portion is only single electrodes here, not paired. So this will allow the tip to bend as per the curvature of the scala tympani of the cochlea. So this is called as a flex tip range here. And the split electrode is for the cochlear ossification. So we have lot number of electrodes. Now what to choose? It's difficult to choose an electrode which is suitable for all situations. You have to choose an electrode which is near ideal to the situation given. Now the decision as to choose an electrode comes from these factors: whether you are dealing with a normal or an abnormal cochlea, whether you are aiming at a hearing preservation or electroacoustic stimulation. You should always aim at hearing preservation, whatever be the case. How much length you want to insert the electrode? Are you going and planning with a round window, extended round window, or cochleostomy? A few electrodes are designed specially for these techniques of round window or cochleostomy. Whether you want to use a straighter one or a pre-curved one, whether you want a half-banded electrode that is directed towards the modulus, or you want to go with a full-banded electrode. What is the thickness of the electrode to the apex to the base? What is the insertion technique or the strategy you have in your mind, whether you want to go for a freehand technique or use an insertion tool? Are you dealing with any special situation like a common cavity deformity or labyrinthitis ossification, where you may go for a shorter electrode, or you can also go with a split or a double array electrode? Are you dealing a fresh case, or are you going for a revision or a reimplantation? What is your experience? A surgeon who has got less experience can better go with a electrode that can forgive mistakes and that can be used with an insertion tool. What exactly is the support and what is the electrophysiology involved? A few manufacturing companies, though not FDA approved, do not support intraoperative electrophysiology. So intraoperative electrophysiology is maximum given by Cochlear company, and the finances is though last factor as a major factor here. So we have discussed about the electrodes. Now we are not using electrode now. So we want no trauma or less trauma to the intracochlear tissues. So I'm taking out the electrode. Instead of electrode, we will be using optical lasers or a mid-infrared lasers. These are coupled with a diode laser that can stimulate the end auditory nerve fibers. Once the optical light or the laser goes from the round window towards the spiral ganglion cell via the cochlea or cochlear fluids. So this is called as optical laser. So what happens is, when you stimulate the auditory nerve fibers with a lesser frequency of somewhere around 150, the speech discrimination is not that great. But
so
if you,
Satya, just to interrupt you,
yeah,
we are short in time, so if you can wrap it up, they have another talk at
yeah,
6.
this is the last slide. This is the last slide.
Okay.
So once you aim at higher stimulation modes, there might be some heat generated that can cause a photochemical reaction. So that is again questionable. So there's still an experimental stage. If you are not introducing any electrode and not implanting the cochlea, do you really need to call it as a cochlear implant? No, you cannot call it. You need to call it as a cochlear stimulator and not cochlear implant. So that is all we have. Thank you very much. I don't know whether I crossed my time. So I'd be happy to take the questions.
Okay, actually, they have a presentation at 6 o'clock. They'll be using the same chat room. So
Okay.
I have noted all the questions. So I request
Okay.
the participants, we have another talk tomorrow by me on cochlear implant complex cases and extended indication. So we'll take these questions tomorrow, which is at the same time at 4 o'clock. We have noted all your queries.
Yeah.
And you can also post questions on the same topic tomorrow also. We will give a short time for the discussion of today's talk. Thank you all, and thanks Satya for the in-depth presentation. A lot of congratulatory messages for you. I think it was a good talk.
Thank you.
All.
Thank you.